So our first speaker is Peter Baddoo. So Peter did his undergraduate in mathematics at Oxford and his PhD at DAMTP in Cambridge, where he was supervised by Lorna Ayton. Following that, he joined Imperial College, first as an early career fellow of the LMS and then as an EPSRC doctoral prize fellow. He's won best paper awards from the AIAA and the ICA, and his PhD thesis was recently turned into a book by Springer. And from January, he'll be an instructor at the Department of Mathematics at MIT. So take it away, Peter.
Thanks, Steve. Our world can often be characterized as repetitive or cyclical. And you might be particularly aware of that during the lockdown, as it can seem that we're living the same day over and over again. Since mid-March, it can be as if there's no difference between the days at all. And as fluid dynamicists, we often exploit this periodicity to learn something about the physics of a system through, for example, Fourier analysis to understand resonance. But it's not just periodicity in time that we're interested in, as we've seen in the lockdown example, but also periodicity in space. And there's a huge number of examples, both natural and man-made, that can be modeled as periodic in space. And during my thesis, I was particularly interested in this example at the top right, the aero engine. And aircraft noise, well, it was a big problem. It's not at the moment, but strangely, we hope it will become a problem again. And I was particularly interested in turbomachinery noise, so how this part of the machine creates noise. And as you can see, this engine is an incredibly intricate and complicated piece of kit. So just improving our understanding by a small amount could be really valuable. And if we look at the compressor, like this yellow box, and squint and put on our applied mathematician goggles, we might see something like this. So this is very roughly what's going on inside the compressor. There's two sets of blades, a set of rotors that are rotating, and a set of stators that are stationary. And if you're interested in the aeroacoustics, in other words, how turbulence generates sound, then you'd be interested in this particular side of the problem. So we model the aeroacoustics problem using the convected wave equation. But before you can understand the aeroacoustics, there's a more fundamental fluid dynamics problem you need to understand, namely what I call roughly the aerodynamics problem. And you need to understand the aerodynamics before the aeroacoustics, because the aerodynamics determines how the background flow refracts sound via the mean flow gradients. So the plan for the thesis was to take a solution for the aerodynamics problem and just plug it into an aeroacoustic solver. And it probably took me over a year to realize that the mathematical structure of this problem, of the potential flow through a cascade, a periodic array of boundaries, the mathematical structure was relatively poorly understood. And it was actually surprisingly difficult to construct the solutions that I needed. So there was this big gap in both the mathematical and fluid dynamics knowledge for this apparently very innocent and very simple problem. And therefore today I'm going to focus on this red box, the so-called aerodynamics problem. And I'm going to explain how you can construct analytic solutions in the sense that you can write them down with pen and paper for potential flows through these periodic domains. Back when I was first learning fluid mechanics, one of the first problems that we were presented with was the potential flow past a Joukowsky aerofoil, such as this one illustrated here. And the way we were taught was that there are basically two steps to solving this problem analytically. The first is to construct a special coordinate transformation, a conformal map that relates a simple domain, a nice domain such as this one, to the physical domain of interest. And because of some of the nice properties of potential flows and conformal maps, the problem, it turns out, is solved if you solve it in the circular domain and then map the solution to the physical domain. You can get plots like this for the streamlines and the perturbation velocity. So there are two ingredients to this problem. The first is the conformal map from the nice simple domain to the physical domain. And then the second is the solution to the fluids problem inside that physical domain. And when I started the PhD, there were no constructive procedures to get a conformal map for this periodic cascade, this disconnected array of objects. So I couldn't make progress in this way. And anyone who's who's actually tried to construct a conformal map will know just how difficult it is to get the precise one that you want. But fortunately, there are special formulas known as Schwarz-Christoffel formulas or Schwarz-Christoffel mappings that are constructive formulas you can use to get the desired conformal map. And they have a long history going back around 150 years, but the most basic version of the map transplants the interior of the disk, like on the left, to the exterior of a polygonal domain. Here I've just illustrated it as a square, but it could be any n-sided irregular polygon. And because we're going from a bounded domain to an unbounded domain, there's a point, this blue dot, that's mapped to infinity. And this is a big result in complex analysis, and it's quite fundamental geometrically, because what could be more simple than the relationship between circles and polygons? Well, it's not really appropriate for my problem because there's only one boundary here. I want a periodic array of boundaries. A big advance came in the early 2000s when my colleague Darren Crowdy and another group independently found multiply connected versions of the Schwarz-Christoffel formula. So by multiply connected, I simply mean that there are just multiple boundaries in this physical domain. And you can see we've taken out some circles in this circular domain, and the colors show the correspondence between the circles and polygons. But one of the particularly attractive things about Crowdy's solution to this problem was that he phrased it in terms of some special functions called Schottky-Klein prime functions. And I'm not going to go into all the details, of course, but the headline is that every circular domain has an associated prime function. So for example, in the simply connected case for the unit disk, the prime function, which is a bivariate function, is just the difference between its two arguments. In the doubly connected case, here taken to be the annulus, the prime function is this more complicated product, and then there's also a multiply connected version as well when we have more circles out. And Darren actually published a book recently. I keep my copy close at hand, and that really goes into a lot of the details of the prime function and also lots of applications. But nevertheless, this is still not appropriate for my problem because this is just for finitely many boundaries. I want an infinite and periodic array of boundaries. And actually last year, Darren and I published a periodic version of the Schwarz-Christoffel formula that allows you to conformally map these nice circular domains to these more complicated periodic polygonal domains. And again, it's valid for multiply connected period windows, as I've illustrated here. And one interesting thing that I can point out is that now not just one point is mapped to infinity, but two are. There's like a left infinity and a right infinity. And this is a branch cut in the language of complex analysis, and that accounts for the multi-valued nature of this mapping function. And this is how the map looks in the simply connected case, but it is valid, of course, for higher connectivities. And just as a brief aside, the mapping also works for these types of boundaries where it's unbounded in one direction, and these when it's bounded in both directions. And you can read about the mappings in detail in Proceedings of the Royal Society. So now that we have these mappings, we can actually use them to construct solutions to potential flows in interesting domains. One of the conformal maps that you can actually write down analytically is this periodic parallel slit map. So this is really an analogy to the Joukowsky map, except it's periodic. And you can see here we're mapping the interior of this disk to the exterior of these parallel slits. And because, well, if we want a uniform flow in the physical domain, it turns out that that corresponds to a kind of vortex pair with a source sink structure in the circular domain. And I phrase these solutions in terms of the Schottky-Klein prime function, and that means that they're valid for any connectivity. These are the preimages of infinity, one to the left and right, but these are the, this is what happens if you take out a disk, we get another boundary here, take out another disk, we get another slit here, and so on. One of the really cool things about this formulation is that it's valid mathematically for any connectivity. So 1, 2, 3, 4, 400 million boundaries per period. Mathematically, it's all the same, although of course there are computational challenges in very high connectivities. And you can include more physics in this problem by accounting for vorticity. So if we want to include the effect of the discretized point vortices, we can just plop some vortices, the multiply connected vortices in here, and you can see how they change the flow field in the physical domain. But this picture on the right-hand side might be alarming to you physically. I mean, maybe all potential flows are alarming because of the lack of physics, but there's something particular about this picture, namely that the flow goes around the trailing edges of these slits. And that indicates that the fluid velocity there is infinite, which is an artifact of the fact that we've neglected viscosity in the potential flow formulation. So in order to address that, we use the Cutter condition. And in these circumstances, the Cutter condition states that the flow should leave the trailing edges of these blades smoothly. And that amounts to specifying the circulation around each of these slits. So if we apply that, the picture changes to this, and you can see just visually inspecting, the flow does indeed leave each of these slits smoothly. One interesting feature to this plot is that you don't get in the non-periodic case, is that there's a completely different inlet angle and outlet angle. And that actually arises due to conservation of momentum. If there's a force on each of these blades, then the fluid has to be accelerated, and that acceleration is this change in direction. You can read about some of these results in this paper. If you're interested in how the mathematical solutions actually look, they look like this. Again, phrased in terms of the prime function, very neat, clean formulas. This first line is the uniform flow contribution. This second line is the point vortex contribution. And this third line specifies the circulation around each of the plates. But because we have the Schwarz-Christoffel formula, we can study more general geometries, not just these slits, which are really degenerate polygons. So here are some examples of the kind of flow features you can look at using the Schwarz-Christoffel formula. Obviously, I'm illustrating the streamlines and the perturbation velocity. You can study polygons with lots of sides, so they approximate circles, and the polygons need not be convex nor regular, so you can do this L-shaped thing. And here's an example of an actual configuration that might appear in a turbomachinery stage where you have these highly cambered blades with non-trivial geometry and some embedded point vortices. Speaking computationally, the maps take usually much less than a second to evaluate, and then I'm using some cool new technology called AAA compression that's based on rational approximation theory. And again, because we phrase things in terms of the prime function, our solutions are valid for higher connected domains. So here's an example of a doubly connected problem where you have this periodic array of boundaries, but there's two different boundaries per period window. And you can also find configurations where these vortices are trapped, like between this doubly connected array of triangles. So these vortices are stationary, but more generally studying the dynamics of vorticity is really important in flow control and turbulence modeling. And these new maps and the new solutions can give new insights into how we can model vortex dynamics. So here's an example. If we're modeling discretized vorticity, we can construct something called the point vortex equation, which governs the trajectories of vortices in the physical domain. But computationally, the forcing in this point vortex equation is very difficult to compute because the forcing is actually the solution to a PDE, and the parameters are changing, the positions of the vortices are changing, so you have a new PDE to solve at each time step. But we can use our mapping formulas to map to a simple domain where the dynamics are straightforward. We can construct them analytically, and then do your integration there. So that's illustrated here. So in the zeta domain, this circular domain, we can construct the forcing analytically and then map it into the physical domain. And you can plot the trajectories after integrating. So this is attractive both computationally because of the reasons that I mentioned, but also analytically, because now we can probe and understand and interrogate this forcing on the right side. If you're not interested in these polygonal domains and you purely want a numerical solution, I've been working on a numerical solver for potential flows. It's based on something called the lightning Laplace solver by Abhigopal and Nick Trevethan. The basic idea is to expand things as rational functions and then solve in a least squared sense. And here's some of the nice plots you can get. And clearly it's very fast. in terms of applications, there are really loads of directions that you could take this work in. I mean, the potential flow approximation appears often in asymptotic problems, either as an outer solution or a leading order solution. And you could extend these subjects to periodic configurations and multiply connected periodic configurations. Physically, what's really missing is the flow separation because we've ignored viscosity, but there are a few new models that you can use to study those, especially data-driven models and network-based vortex modeling. And as I wrap up, I'll just explain where this project fit in with the rest of the thesis. I really considered 3 separate scenarios: a thin aerofoil scenario, porous aerofoil scenario, and this multiply connected scenario. And I looked at them from both aerodynamic and aeroacoustic perspectives. So I used quite a few techniques, mainly from complex analysis, so things like Riemann-Hilbert problems, singular integrals, Wiener-Hopf, and we heard about the conformal mappings just now. And to finish, I have to acknowledge Lorna. I was her first student and she did a phenomenal job supervising me, and many other people were also really helpful during my thesis. So thanks for the opportunity to speak, and I'll be happy to take questions.
While they're doing it, I could possibly ask a question. So you have this formalism for an infinite array of periodic devices, if you like. But presumably in any engine, of course, you do have boundaries. But the original methodology worked for that. I guess you could put as many polygonal things in there as you like. So have you looked at the difference between an infinite array and a finite array?
Well, really, what we're doing is basically unwrapping this turbomachinery. So
okay.
It is actually periodic.
So it is periodic. Okay.
But it's got that
okay.
radial symmetry. Yeah.
Yeah.
So the important thing is that the radial component of the flow is not that significant, and then you can make this 2D periodic approximation.
Right. Okay.
Hey, Peter. I really enjoyed the talk. Quick question. So how easy is it to extend this formulation if the wings inside your periodic box have different kinematics? So let's say if they're moving with different velocities.
So if like this wing is moving at some phase and then this wing is a slightly different phase, I think that mathematically those solutions, well, I don't want to say they don't exist. I haven't seen anything like that. I think you need to inspect like whether those sums actually converge. I think in terms of Helmholtz, if you're looking at the compressible case, there are definitely solutions to that, and you would phrase those in terms of the quasi-periodic Green's function, which I looked at towards the end of the thesis. But at the moment, I'm not confident that you could do that without compressibility in this potential flow framework.
Which says, have you checked how it compares with real life fluids in cascades?
No, I haven't compared to any experiments because, I mean, obviously nothing is actually periodic in real life. I would really like to get some data that could be used to verify how useful these frameworks are. But also a really valuable thing would be to include these other physical effects that I mentioned, because flow separation is really going to be important in practical instances. So I'd love to incorporate those features.